It's my great pleasure to introduce our first speaker and a very dear colleague of mine, Ilya Sergey. Welcome, Ilya. So Ilya is an associate professor at NUS in Singapore. Before that, he was at UCL in London. He did his postdoc at IMDEA in Madrid. His PhD in Leuven, right? And so he has traveled around the world quite a bit in his career, and also topic-wise, he has worked on many different things. He's very well known for his work on program verification and program logics, especially also for distributed systems. He has worked on program synthesis. He has done a whole lot of work in the space of smart contracts, how to design smart contract languages, how to reason about smart contracts. And today he's going to talk about how to efficiently execute smart contracts. Just as a piece of trivia, he's also well known for probably the most famous slide in program verification. So he has a slide that gives an overview of different separation logics, which I think dozens of people have used in their talks. And that's also by him, so another important contribution. So it's great to have you here. Welcome, and please go ahead.
All right, so first of all, this is my first time in Zurich and in ETH. I'm really, really thrilled to be here. I want to start by thanking Peter, Jiandong, Martin, and Markus for organizing this fantastic workshop and given an opportunity to travel to Switzerland and enjoy the great audience and also give a talk here. All right, so as mentioned, my talk is going to be on smart contracts. Well, not really verification, but applying formal methods for something which I believe not a very explored area in this space. Well, effectively for improving performance of distributed systems, blockchain protocols that are used to execute smart contracts. And this is a work that I'm very excited about. It's still an ongoing project, and the main spearhead on that is my PhD student, Georges Perlet, who is also the first author on the relevant papers. All right, so let me start by talking not about smart contracts and not about static analysis, but on distributed systems. So how do we go about implementing a performant and a robust distributed system? So the recipe for that is actually quite well known, and it has been perfected over the years. First, the Turing Award winner Leslie Lamport came and in the 70s published the paper on time clocks and ordering of events in distributed system. And the recipe for building distributed service was simple. So first of all, if you care about your data being present in multiple nodes, you need to replicate the data. And now we have multiple replicas. And then if you want to modify this data, you need to make each replica execute an identical log of operations going one by one. And in doing so, the replicas really need to communicate the order of operations to each other, so updates would be consistent. And that was working until people realized that the replicas might fail. And then the second iteration on the idea of robust distributed service was by another Turing Award winner, Butler Lamson, who came over and said, well, we already have these nice consensus protocols, actually some of them by Leslie Lamport. Many of you are probably familiar with the family of Paxos consensus protocol. So let's just plug the consensus protocol in, and so it would be able to tolerate certain number of faults in our system, and start using this consensus protocol as a way to agree on each step of execution or even multiple steps of execution. So now we can keep this log consistent even in the presence of certain benign failures in our system when suddenly, for example, the node stops participating and stops responding. Well, the story keeps going on from there. Next, Miguel Castro and Barbara Liskov, yet another Turing Award winner, came over and said, well, but what if we have the nodes that don't just go offline? What if we have the nodes that behave maliciously as bad actors and try to confuse other nodes? In this case, we can revise our consensus protocol to make them robust to what's called the Byzantine general problem, or in other words, making it Byzantine fault tolerant. Many of you are probably familiar with this 99 famous paper called Practical Byzantine Fault Tolerance. And again, this is all great, and these protocols, they got a lot of attention recently, but there is still one issue that these protocols, they assume what's called the closed ecosystem. So effectively, in order for these protocols to work, we need all the participants to know of each other identities, and it's very difficult to change the set of participants in this protocol. Typically, you need to run yet another protocol for reconfiguration. In order to make this process more lightweight and make these protocols open, so anyone could join and participate in our distributed service, well, a very prominent idea which got a lot of hype, both positive and negative, for its environmental impact, is to use what's called Nakamoto consensus, published by the pseudonymous author, and many of us know it as the initial Bitcoin blockchain protocol. So the key of Nakamoto consensus is now that our consensus protocols, they are not just Byzantine fault tolerant, they are also open, so people might participate, and the replicas remain consistent even in the presence of what's called forks, as long as we have the majority that follows the rules of the protocol and doesn't go offline. And we are almost there, but in the most modern history, people were interested in using those protocols not just for a certain set of predefined computations, they actually wanted to have something even more versatile and put arbitrary computations on top of the blockchain protocol. And the last idea came here, popularized by a number of authors, most prominently Gavin Wood and Vitalik Buterin, who came up with architecture which is known nowadays as Ethereum. And the idea is that now our transactions and our logs in the consensus protocol can carry arbitrary logic, so they can implement arbitrary user-defined replicated computations, and in order to avoid denial of service attack, the important component of Ethereum that it also comes with the cost semantics. So one, when proposing certain computations to be performed, also needs to pay a price for it, and this is a deterrent against running something very, very computationally expensive on the other's machine. So that was a brief history of distributed systems, culminating with the rise of programmable blockchains, which has been embodied by Ethereum, but now obviously there are dozens of such blockchains with different ways to program them. So what are the key problems from my perspective? And here's something that we can probably disagree on. I'll be happy to have a discussion. What are the key problems in the space of programmable open consensus protocols that are blockchains? So the first problem is that one of correctness. So if we have arbitrary replicated computations on the consensus system, and those computations are known as smart contracts, they obviously can be buggy in thousands of possible ways, and in the in really bad scenarios, they can freeze certain digital funds associated with the state of these computations, or even worse, they can lead for exploits. And obviously the problem of correctness, which is so dear to the hearts of verification researchers, got a lot of attention in the community, especially after the infamous DAO reentrancy attack that took place in May 2016. So there were hundreds, if not thousands, of papers published about how to mitigate those bugs, how to detect them using static or dynamic verification, and even on how to repair smart contracts. So these are the two most famous and two most important bugs, which sparkled a lot of research, and it's still going on, and it's a very popular research area. So that is about correctness, which is probably would be closer to the topic of this workshop. But as a diversion, I decided to talk about a different problem, which got way less attention, at least in the formal methods community, and that is the problem of scalability of the consensus protocols that can run arbitrary smart contracts. So the problem with traditional consensus protocols, and in particular with blockchain protocols, that they are really, really slow due to the decentralized nature. And this is something which is a little bit counterintuitive, because one inherent trait of distributed systems that, well, they are concurrent and therefore should allow for parallelism. But this is something that doesn't quite work in the case of consensus, because if you have the consensus, you are actually expecting many replicas to agree on a certain next operation to perform, on the next transaction or a next execution of a given smart contract. And the more replicas you have, typically the slower your consensus becomes. And this is particularly so in the case of blockchain. So as of a few months ago, Ethereum's throughput, so now things have changed slightly because the protocol has been changed, but a few months ago, Ethereum's throughput was not even close to that of traditional financial systems, such as Visa or MasterCard. So Ethereum only could process 11 transactions per second, which is obviously something that you want to improve. And furthermore, more than once, the system saw the scenarios where a single popular decentralized application, The most famous being CryptoKitties, the game where you can trade with funny images of cats using the native currency of the system. So that effectively was the contract that hogged the entire processing capacity of the system for a few hours or days, and it caused congestion that much that no other transactions or no other applications could really run on that. And also the code semantics had to do with that. So this is a serious issue. So, and if we want this system to survive and eventually compete with traditional financial systems or be domain-specific distributed computers, which is what Ethereum has been initially positioned as, well, that's the scalability issue, is something that we also need to address on par with ensuring correctness. And obviously there was some research in the distributed systems community proposing a number of protocols, and my interest in that as of a formal methods researcher. So what exactly do formal methods have to offer for helping the scalability issue in blockchain consensus protocols? So let's look at the crux of the problem. So here is the problem in the nutshell. So this is what are the main bottlenecks in blockchain consensus protocols. There are two of them. So one of them is state, and another one them is execution time. So typically the way this protocol works is that it has a system of nodes that communicate with each other in order to reach the consensus, and there are external clients to the system, which might as well be the same nodes, that initiate transactions in order to change the replicated state. Remember, we are dealing with the replicated state, so the change to state in the system. So when a transaction comes, it usually gets routed to all the nodes, and all nodes are supposed to have the entire replicated state in order to execute this transaction, because we might not know upfront what exactly are the parts of the replicated state that this transaction will touch. Furthermore, since we are interested in the global consensus, and global consensus is something that comes only when we have the majority of certain kind of the nodes agreeing on which is the order of operation and what exactly are the operations that we are going to process. So because of that, each node also needs to execute every single transaction. And now you see, so state obviously keeps growing, and the more transactions we have, the more transactions we need to reach the consensus, and reaching consensus even for one is quite expensive. So this is the reason why adding more nodes to the system doesn't really increase your parallelism. It doesn't increase your throughput. In fact, it slows down. And it also doesn't quite allow more state to be stored. So obviously, these are the two bottlenecks that we can address using certain techniques. And let's see what are the implications of that. So since I've mentioned Ethereum, so the snapshot of the state that you need to run an Ethereum node for now, even like without the whole history, just the current state that you are going to start from in Ethereum, as of November last year, was already 130 gigabytes. And since we are working a lot with the state, ideally you would like to keep the state in a fast memory. So prepare to have a lot of RAM if you want to make the system very performant. And in fact, well, you can also use something fancy like non-volatile memory. And the reason for that is actually one of the main bottlenecks in Ethereum execution is the time that's spent performing the input-output of the disk. So research in non-volatile memory obviously is going to help, but that's going to be complementary to the research on speeding up the protocol itself. And increasing hardware node requirements, and this is something more of economical aspects, actually decreases decentralization. Why is it so? Because if you have a distributed protocol, which is quite cheap to run, though, so you can just join it with your phone and start running your node, that's very appealing. That's actually the main promise of decentralized trust. So we don't really have a small number of authorities that control what is happening in the system. But the more and more you increase the requirements, the more beefy machine you require to run the node, the less is your decentralization. So eventually, in the worst case scenario, we can only have a few parties that are capable to take decisions which transactions are going on to be accepted next. And this is obviously something that is at odds with decentralization, which is, for example, which is, for example, one of the criticisms that this is a system that recently came to a lot of prominence called Solana got. So Solana, I think it's now like 6th or 7th in the market capitalization, and it's very fast. But the point is that there are not that many nodes that can run as validators for Solana. There are only a few dozens of those, precisely because of these requirements. Okay, so if you want to keep the system kind of decentralized, then the sad reality is that the throughput for execution of your transaction is limited by the capacity of the least performant node. So obviously that might be the node that can be just discarded, but that weakens the chances for the consensus to happen, because that obviously, if we have Byzantine nodes to have more power, well, that's pretty bad for our system. Okay, so people obviously recognize this problem, so what has been done up until now, and what is the state of the art in scaling the throughput of blockchain protocols? So there are actually two big families of solutions, which in the community traditionally addressed as layer 1 solutions and layer 2 solutions. So the layer 1 solutions have to do with taking a good look at what essentially used to be Nakamoto consensus protocol and then enhanced with capability of executing smart contracts and revise the rules of such consensus protocol, so in a hope to increase the throughput. For example, mining and computing the reverse hashes in the proof of work used to be a huge bottleneck and also not friendly to the environment, and this is something that has been addressed in many systems. Many of you might have heard that 3 weeks ago Ethereum had emerged when they switched the system to the proof of stake, which is more environment friendly, but also more performant, given that you manage to synchronize the clocks in most of the nodes. So another approach is very much inspired, as pretty much anything in systems designed, by the advances in databases, and this is called sharding. So and sharding is going to be the main topic I'm going to talk more about in just the next, starting from the next slide. But the idea is that effectively we try to structure the execution of our system that it has some inherent parallelism in it. Okay, so but for completeness, let me also mention something that is coming to prominence now as we speak. So that's what's called layer 2 solutions. And the idea of layer 2 solution is effectively compose different consensus protocols. So some part of the execution can be uploaded to some other protocol, so the key protocol doesn't have to bother with that. So there are actually two main ideas there. One is to compose blockchains. So nested blockchains is when we use the main consensus protocol only to store like the big deltas of the state updates that otherwise managed by smaller side chains using these transactions. And probably the largest example of this protocol is the Plasma proposal for Ethereum. And there is also an approach which probably would be of a large interest for programming language community, is the one based on off-chains executions, when actually the execution of the smart contract logic is not validated by all the replicas, but rather is executed by a small subset, and then the results is what is presented back to the rest of the system. And obviously this opens, I see the hand Zach, so that opens a large space for the abuse. And these mechanisms, they differ based on how exactly the validation of this off-chain execution is done. Some of them are using the zero-knowledge proofs, and some use what's called optimistic rollups when the results are challenging and then they are executed on-chain. I'm not going to go much more into the details. The thing is that both of these models, they somewhat limit the expressivity of programming language model. They limit the amount, the number of classes of applications that you can implement and execute off-chain. So, Zach, you had a question.
Yes, I was wondering, do any of these solutions exclude each other, or are they all complementary, or?
Great question. So Zach is wondering, are these solutions mutually exclusive? The good news, no, they are not. You can have a layer 1 solution that speeds up the execution, for example, of your main chain or of validation transactions using optimistic rollup, and you can also have side chains. And as far as I know, there are systems, although I don't remember the names, that experiment with that. So if you want to see solutions for optimistic rollups, you can look up systems such as Optimism and Arbitrum, developed at Princeton at the moment. Thanks a lot for the question, also giving me the opportunity to get some water. All right, so let's talk about tier 1, a solution which is quite prominent and also has a lot of degrees of freedom to exercise, called sharding. So the idea of sharding is very simple. So effectively, instead of having one monolithic system composed of all the nodes in there that validate every single transaction, we are going to pretend that we have sort of a parallel computer. So we are going to split the system into a number of smaller sets of nodes, such that each such set of nodes runs a small consensus protocol only for a subset of all transactions that come to the system. So, and each shard executes as a set of transactions, and then using a certain other protocol, typically something much cheaper than the full-blown consensus, using something like two-phase commit or just simple three-way merge, in case if we can prove that our transactions are non-conflicting in these shards. So then these transactions are being merged together. Okay, so this is kind of a very simple idea, and obviously you are expected to give linear throughput scalability with increasing the number of shards, and you somewhat sacrifice the security conditions a little bit, because now you have a chance of a small shard to have a larger fraction of Byzantine parties. But this is the risk that people are willing to take, and in practice they are not very large. Okay, so that is something that can be done surprisingly easily for transactions that only have to do with updating accounts with currency. So when Alice transfers a certain amount of money to Bob and vice versa. So there are sharding strategies for that have been exercised in the past. But here we are talking about arbitrary code. So we have smart contracts that can execute arbitrary computations, and this is where things start getting really tricky. Because now we have the contract, which is effectively a piece of state that is governed by a number of functions that different transactions might invoke. And how do we get the parallelism if we have smart contracts? So the simple idea is to sort of have a fallback strategy in which we can execute all the transactions for a certain contract sequentially, but otherwise what we can do is to assign each contract as a certain object with its state to the shard. Well, as long as we have transactions that only touch one such object at a time, or the transactions that do not require the smart contracts to communicate with each other, we are good. So we are still in the disjoint world where everything is parallel. And in fact, all the systems that implement sharding of some smart contracts, they sort of exercise this solution with a fallback strategy that if actually we have a transaction that touches multiple contracts, or a transaction that requires the contract to communicate with each other, there is also a separate stage in the protocol in which all these transactions are processed. Usually this stage goes after the parallel stage, and then they interleave. And obviously there is not that much parallelism in this case. So it turns out that this solution doesn't address one of the most paramount problems in this space. So what if we have a contract which implements a coin which is very popular? So now many people want to invest, or many people want to trade with this token, and this token is assigned as a smart contract to a particular shard. So now we have thousands of transactions that are all getting routed to the shard that keeps this token, and obviously that gets congested very quickly. And the worst thing that, well, we actually don't get to redistribute this load across the whole system of shards in the system. So we don't get that much parallelism of it. And why this exactly is a difficult problem if you come from the perspective of the protocol designer? Well, as a protocol designer, you actually don't know that much about what your smart contract is doing. So for you, it's a black box. So, and the best you can do is to assign it like this to one shard and hope that you don't get that many transactions. But imagine if you have a way to see what your contract is doing. So maybe that will give you an opportunity, instead of assigning one contract per shard, to actually split the state of this shard and also the logic of this shard in a way that now it can be handled, of this contract in a way that it can be handled by multiple shards. Okay, so now the problem kind of becomes clear. How do we get the idea of what kind of inherent parallelism is enabled by the structure of these contracts? Or if you're familiar with the way of thinking in terms of concurrent data structures, which operations of contract, being a data structure that can be modified concurrently, do commute with each other and can be executed without introducing conflicts deterministically in this pessimistic parallelism way. So we know that we can always run them in parallel, and we always will get the same result when we reconcile the state of the contract. So this is, I think, was the aha moment of this work, when we realized that by looking at the smart contract not just as black boxes to which you send the transactions and you hope that no conflict will happen, but rather by looking at them as two programs that we can analyze. So how can we help to solve the scalability problem in the blockchain? So the key idea of what I'm going to talk about next is to look at the smart contracts code to learn about the opportunities for parallelism and to learn how that smart contract can be sharded. So let me just reiterate the title of our talk. So the problem that we are solving is the scalability of blockchains that involve smart contracts. And now the tool that we are going to use, which comes very much from the formal methods and verification community, is the static program analysis. And I've already gave a few hints about what exactly properties of our smart contracts we are going to infer using static analysis. So those properties have the names. One of them is ownership, and another is commutativity. And in a couple of slides, I will elaborate why those are important for parallelizing smart contracts. Okay, so I believe most of you here are familiar with some idea why static program analysis is such a prominent technique in programming languages and formal methods. So using static analysis, we can derive properties of the programs that hold regardless of which input to the program we provide. And that has vast opportunity for verification and validation, the main topic of this workshop. So having a specifically tailored static analysis, you can determine without running a program and soundly prove the absence of bugs in it. There are not that very many static analyses that deliver on this particular guarantee. One well-known is the Astray static analyzer by Absinthe. And a more prominent modern trend is to use static analysis to soundly show the presence of bugs as a drop-in replacement for fuzzing and testing framework. And I believe the talk which will be after this one is on the Pulse X framework by Azalea, who will tell how to design and use such analysis for bug detection in practice. So stay tuned. However, those of you who are proficient in engineering optimizing compilers know that probably one of the main benefits of static analysis is to soundly infer information about programs that can be used for optimizations. Starting from something as simple as constant propagation, inlining, or static method dispatch in object-oriented languages, going further to automated parallelization. And automatically parallelizing compilers for something as old as Fortran, the language, they're very much a thing, but there are no parallelizing compilers for smart contracts in the blockchain. And this is exactly what we are going to build. So we are going to apply the formal reasoning as a tool for uncovering opportunities for scalability, and we are going to make this static analysis an inherent part of our consensus protocol. So the key novelty of our work is that we don't look at smart contracts and the analysis for them as something that is only inherent to the language layer. Rather, we make it a part of the protocol that will take advantage of this static analysis to maximize its throughput. So let's see how exactly these properties are manifested in practice and how can we use them. So for that, I'm going to use this slightly contrived example, which nevertheless illustrates the two main phenomena that can lead to better parallelization of smart contract execution. So here is the smart contract implementing a token, so some user-defined currency, and well, there is certain amounts of this currency assigned to users that currently have presence as records in the state of this contract. So Alice has 10 tokens, Bob has 25, and Charlie has 12. And also we have two different ways to interact with the smart contracts and alter its state. One is to buy certain tokens and register the user in the system by means of saying who is the buyer and transfer a certain amount of money. And another is to exchange tokens between the two accounts, making a transfer from one account to another one. So it turns out that these two transitions, these two ways to interact with the contract, will be sufficient to show what exactly we can parallelize. Okay, so let's look at the first scenario. So when we now have Alice, Bob, and Charlie, and some of them want to buy new tokens because, you know, the price is growing. It would be nice to own some. Not exactly the case now, but back in the days, that's what people were mostly doing on the blockchain. And obviously, they were very upset when they couldn't do it as fast as they could because, well, you know, Ethereum only takes 11 transactions per second. Okay, so how can they do that better? Well, they can do that better if each of these users is assigned to a separate shard. Well, does it look familiar? Well, it kind of does, because before we assigned a contract to a separate shard. So now, instead of assigning the contract, we are sort of assigning slices of the contract to the same shard. And it doesn't mean that the state gets replicated, the state gets sharded too. In fact, the state can be very much replicated. But the idea is now different shards are responsible for modifying the state that is associated with these particular accounts, with these particular components. So in other words, this transaction buy tokens, which requires an identity of the buyer and amount. In fact, it has, and people who know separation logic will probably appreciate this analogy, it actually has very specific small footprint. So it only cares about one particular account, the one whose record is going to be modified. So if it's Alice who is purchasing 5 tokens, then this transaction can be dispatched based on the identity of Alice's key in the representation in the map into this shard. And if it's Charlie, obviously it can go there. So what does it have to do with the properties of the program? Well, effectively, by looking at the code of buy tokens, we need to say what exactly is the footprint in the state of the contract that it requires in order to run, in order to succeed, and in order not to conflict with other similar transactions. And that footprint is something that we typically call a state that needs to be owned in order to execute this transaction. And this is exactly what is going to be uncovered by the ownership analysis of the corresponding transition of the corresponding contract. So far, so good. So we earned ourselves some disjointness. And whenever we have disjointness, real or abstract in this case, we have parallelism. So that's great. Okay, let's look at more complicated scenarios. So things actually not always strictly disjoint. So sometimes we have something like this. So we have something like transfers. So in this scenario, notice what happens. So Alice transfers like this both 5 tokens to Bob for whatever service, and Charlie transfers 3 tokens also to Bob. Okay, now we have transactions that actually require ostensibly ownership over more than one component of the state. So, for example, of Alice and Bob on the left, or Charlie and Bob on the right. However, we can notice how exactly this transaction works. So obviously, we still, if we have multiple transfers from Alice or from Charlie, these transfers cannot be really executed in parallel because in this case, it's very easy for Alice or Charlie, what's called double spend. Make 2 transfers with other shards being unaware, so like the consistency is being validated. But as long as Alice's account is still managed by her shard and Charlie's account is still managed by his shard, and the same goes for all other transactions, things are fine. What about Bob? Well, notice that this transaction, the effect on the account of Bob, is actually just adding some number of tokens to its state. So from Alice it gets plus 5, and from Charlie it gets plus 3, and altogether we can just sum them up and get the result in delta. So does it look familiar? Well, yes. So effectively we have a merge operation here over 2 operations that do compute with each other. So we can, it doesn't really matter in which order we supplement Bob's account with these additions, because these 2 operations compute. And in fact, if we have mechanism to perform this 3-way merge at the end of certain stage at which these 2 transactions took place, we are still good. So we will deterministically get to the same state, no matter in which order we will adopt these transactions. James?
That's true, unless there's failure.
There's a failure?
If there's failure in the system, that what you just said is not correct.
Okay, so the question, what about failure? So here we probably want to distinguish between kinds of failures. So if we have a failure within one shard, then this is something that is typically taken care of by PBFT that runs within this shard. I don't have an immediate answer what happens if the whole shard fails altogether. But presumably in this case, this transaction will simply not make it to the merge state. And then the way the systems they are typically structured, the shards, they're getting reshuffled synchronously every once in a while, every several minutes. So this transaction might have a chance to be processed in the next stage. I'm not sure if this is exactly the scenarios that you had in mind, but we can...
Well, you made a simple transaction that was local into a distributed transaction. And once you go to a distributed transaction, you have to worry about failures. Otherwise, you don't really have a transaction. It has to, either commit atomically or not commit. And you could have, Charlie get debited and Bob not get credited and Bob fail.
Yeah.
And your system is inconsistent.
Right. Okay. So what about atomicity of the transaction? So here I'm not a protocol designer, but this is something that has been addressed by the core protocol implementers who say, well, effectively the assumption is that the atomicity guarantees, they come from the consensus protocol that runs within each shard, namely practical Byzantine fault tolerance. So the idea is that
But the problem is that you need to have atomicity between shards, which you said are independent. So where where is the atomicity guarantee for this sort of multi-shard transaction?
Well, let me try to speculatively answer, but I think that's a good discussion for after the talk, that it's assumed that once the transaction got accepted by the shard, it doesn't fail. So that's when it's effectively persisted. And the only thing that remains to do is to communicate that to other shards, which is what this merge is doing. Sure. Shall I carry on, Martin?
Just something like, so basically, there is a proof probably like this partitioning gives you some equivalency, right?
Mm-hmm.
But I guess the question is, does it depend on the underlying protocol?
Okay, so equivalence. Let me try to phrase the question so it will be convenient for me to answer. So the question is, what kind of consistency does this protocol deliver? And effectively, the consistency or equivalence in your terminology is that the executions of this protocol should be equivalent to the sequentially consistent executions of the global consensus, where there are no shards involved. In our system, it's not exactly the way, but there is one small subtlety that is kind of reminiscent to what people have to deal with in weak memory models, so we can come to that. But in the ideal case scenario, we should behave the same way as the global consensus with no sharding involved. Does it answer the question?
It's like the older robustness conditions in weak memory, right? Like,
yeah. So
that would have to be, it would have to come in.
Right. So there will be one subtlety. Let's revise it in a couple of moments. Good questions. Any others? Wonderful. Yeah, please keep doing that, because this way it's much more interactive. Okay. Now, with some adventures, Bob finally got these 2 additions to his account, so now he owns 33 tokens, and that has been made possible by the fact that such additions of a constant to a certain mutable value, they in fact do compute, and it doesn't really matter in which order we apply them. So when the three-way merge of the effects of these transactions takes place, well, we know that it doesn't, so it always will be deterministic. Okay, so these are the 2 very simple ideas: disjointness, aka ownership, and commutativity. So now we need to discover these opportunities from arbitrary smart contracts, which might be a tad more complicated than this my token. So for that, and this is the key contribution of our work and what George and I have done, is build this static analysis, which for lack of a better name we call co-split. And this is a static program analysis that infers properties of smart contracts that make them parallelizable or shardable. So this analysis is unfortunately not super generic, so it's implemented for one particular language and is deployed on one particular system. So the system it has been deployed in is one of the few production-ready systems that actually has sharding capabilities, but its initial sharding strategy was somewhat naive, namely assign one smart contract per shard, and if there are conflicts, then just move that to a dedicated shard. And the language that we build in is the language called Scylla. That's the language that we have designed for Zilliqa, and it has a fair amount of users. There are several thousands of contracts written in it. It's nowhere, obviously, as popular as EVM, but this is a language which is designed to be minimalistic and principled, and it comes with a reference interpreter, so it actually is fairly easy to implement a static analysis for it. And it's also a higher order language, so you can write functional programs in it. So I'm not going to talk that much about Scylla. We actually have an UPSLA paper a few years ago that describes the main design components. The key parts of Scylla is that, well, it loosely reminds of Solidity with an object-based model, but smart contracts in Scylla, they are not objects, they are actors. So in fact, the way you communicate with a smart contract is by sending a message to it, and it can react it by changing its state, and also by sending messages that will reach the clients or the other contracts. In such way, it avoids things such as reentrancy. So basically, every execution of the contract itself, it's non-reentrant, it's atomic in this particular small-scale sense. And secondly, the language doesn't really mix together the effectful and non-effectful operations in the same way languages such as Solidity following JavaScript does. So there is a syntactic separation between pure computations, which involve higher order functions, and effectful computations which have to do with sending messages, updating states, or triggering events. So the language is small, means it's a little bit verbose, and there are some higher level languages currently under development that compile to it. This is what a typical transition of a contract written in Stiller looks like. So we have a mutable field called balances. So this is actually from our example, which maps addresses of the participants to the non-negative amount of currency. And then, okay, I'm not going to go that much to detail, but you can see that in somewhat a little bit convoluted way, it updates the balance of the sender with a new with a new amount by adding it to it. And the reason why there is a lot of pattern matching, so that's the way to represent conditions. So there is no if, there is pattern matching. But that's the analysis, that's the language design point. Okay, so that's the language. And now we need to have a static analysis for that. I don't have super much time, so let me just quickly focus on the points that the analysis delivers. So the analysis produces two properties for the program. One of them is, as mentioned, ownership. And for those who are familiar with the terminology, to derive the ownership over state components that are used by a transition, we actually don't need to do something sophisticated. We just need to run a simple effect analysis that statically derives an over approximation of all reads and writes and also conditioning that has to do with certain state components. For example, something like add money to the balance will have to do with an entry of the state of the mapping that has to do with corresponding amount. So this analysis is loosely inspired by what people do when they're trying to infer specification and separation logic. So they see which parts are updated disjointly, and then based on that, they ascribe the pre and post condition with a star to the program. And then we have a commutativity which is slightly more complicated, and it builds on the observation that effects of monotone operations such as adding constant or multiplying constant, which use a certain field just once by updating it in a particular way, they do commute. So we didn't really extend that for fancier notion of commutativity. That would be something interesting to explore, but some analysis has shown that those kind of operations are very rare. So mostly people just add stuff and multiply stuff. So the interesting part that to track this just once thing, we need to have some sort of linearity/cardinality analysis, and there are systems that do that. So 8 years ago, I had a paper which did a certain analysis for Glasgow Haskell compiler with certain optimization in mind that kind of tracked exactly this property, whether certain values are used exactly once. And with that, you can do some nice inlining, and we effectively took that as an inspiration for building this commutativity analysis. And also this analysis very much resembles a type inference because it infers certain form of types, saying how exactly your transition or your function uses variables. Does it use them 0 times? Does it use them once or more? And if it's so, which operations do contribute to a certain value? Okay, this is something that I'm just going to briefly flash. So this is an abstract domain of the analysis, which effectively collects the effects and also collects all the variables that have been used with a certain continuity, 0, 1, or more than 1, and also the operations that have contributed to a certain value. So you can think simple data flow analysis. This is how it works in practice. So here, let's analyze our method transfer and determine what exactly are the effects of this method and what exactly has been used once or more than once. So from this line, we can see that we have a read from this particular component of a map, and this component is tied to the sender of the transaction. You can think of it as an implicit argument to the method, this underscore sender. So that's why it's not mentioned. So then this sender is also used for conditioning on its value. Then it's used for deconstructing in the pattern matching with no particular operation, but that already contributes a single usage of it. More conditioning, more operations. So now we see that it participates in subtraction with a certain constant, which is amount. So for the duration of this method, this is a constant. And finally, we write to balance the value that came out of the subtraction. So that might look a little bit cluttered at the moment, but the fact that we only deal with this sender field and also the parameters of the transition, this is actually something that will be very crucial to determine that we actually only need the ownership over this field to run this transition. After that, what do? We update the balance of the recipients. So we read from that balance. We add to this balance by using it exactly once a certain amount, and we write the result back to this balance. So effectively, these two separate operations show that this component balances of 2 only participated in an increment, and it only was used once with an addition, which happens to be a commutative operation. Okay, so how is it going to be used? Again, another piece of abstract grammar very quickly. So the way we are going to transform our knowledge of what the transition does is by compiling that to a series of constraints that a certain shard needs to satisfy in order to run this transaction. So this is actually the component where the result of the analysis become relevant to the protocol. Okay, so what exactly is the interaction between the analysis results and the constraints on the shard that can run the corresponding transition? So these are exactly the summaries that we have extracted from our analysis, and I put them into two different boxes to show which pieces of knowledge they contribute regarding to the sharding. The first box on the top, the blue, it kind of shows that we only manipulate there with sender, and also the amount, which is the parameter of the transition. But if we know the sender, and if we know which shard owns this particular component of the heap, and this is something that we can come up with a strategy. So even though we might have multiple senders and they can appear dynamically, we can have, I don't know, a hash function or a solution that always tells us deterministically which shard owns a certain sender in this epoch. So this, in order to run this part of the transition, we only need to own this piece of state. Hence, the constraint which will be emitted to determine which shard needs to run this transition will be written as this shard should own the state component, balance of the sender. And how do we know the sender? Well, because the transaction, when it's formed, the sender is already there, so we can perform lookup for the shard that satisfies this constraint. So, but there is also a second part, which has to do with updating the two component, the balances of two. But for that component, we know that it's being updated in a way that would compute with other similar updates. So for that, we actually don't need any specific constraints. We will know we'll always be able to merge the result of this transaction with regard to two. And that's why, in order to execute this transaction, we only need to secure the ownership over the sender, but not the ownership over the recipient. So, and second, when we have figured out that, we also need to determine how exactly we are going to obtain the new state should several transactions of this kind be performed. So for the component that we need to own, we have the merge strategy called own override, which effectively replaces the old state by the new state, and we know that there will be no conflict because on this piece of state, the effect of the transactions were disjoint. And for the effects such as the commutative addition, we can initiate the three-way merge using the strategy called int merge in green, and this is something that happens for unowned contribution. So we used to have a more expressive language of combinators of these strategies, because if you have pairs or like pairs of integers to which you add, so you can obviously derive more interesting strategies, but these two are really basic ones, and those are the strategies that worked in 90% of the cases. And now coming to Martin's point. So there is actually one non-trivial condition. Imagine that we have Alice giving some money to Bob and Charlie giving some money to Bob. But at the same time, Bob wants to transfer some money on his own. So it might transfer it based on a certain foresight that it will get the money from Alice or Bob. And in this case, that transaction might succeed. However, in our model, these updates, they don't come immediately. So in fact, Bob might not have enough money at a certain moment. So this condition might fail. And this is where we start thinking that our model is not exactly fully sequential, so it's more equivalent to these weak memory models, where we have some updates, we have like store buffers, which might be flushed at a certain point and you will get your effects. And here the analog of flush and store buffer is reaching the point in the protocol when the deltas are being merged and all effects are applying to the state. But if you rely on that, you might not exactly get the same execution because sometimes you can work out of stale state. And this update will only come later. So this is something that is a little bit subtle, and typically when we require the user to shard protocol, we also say whether they are okay to have at least a certain amount of stale state in the transaction, knowing that it will be updated later. So this is somewhat like a weak read in relaxed memory models. Okay. So I am approaching the end of my presentation. Let me just quickly talk about how that works all together. So this is a big scary picture of the Zilliqa protocol, but in fact there are only a few important components here. Here are the lookup nodes that for each transaction determine where it should be processed. Here are the worker bees the shard that they take care of for parallelism. And if the lookup node determines that the node can actually go to a certain shard without posing conflicts up and merge, this is where it goes. And there is a dedicated shard, which is essentially a sequential an unavoidable sequential bottleneck in the system, is the one that tackles all the transactions which we simply cannot shard or that require sequential access to a certain piece of state. And this is where the transaction go if we cannot satisfy the constraints for certain shards or if the transaction actually touches multiple contracts. And the arrows back and forth have to do with all the shards sending their deltas to this DS committee, which stands for Directory Service Committee shard, that performing the merge, and then sending the final block back to the shards at the end of each epoch, which roughly takes about 2 minutes. And after each epoch, everyone again has the up-to-date state for the beginning of this epoch. So that's the model of the system, and this is how the parallelism is achieved through routing the transaction based on the constraints to this different shard. Okay, so what it looks like for the user. So there are actually several components, and from the user's perspective, when you want to deploy a smart contract, you run the static analysis, you get the effects, and from there, based on which transitions you want the system to run in parallel, you get your sharding signature, so which says what can be split, what needs to be owned, and how do we merge. And this sharding signature is actually quite interesting because this is what gets deployed along with the code of the contract. So other miners, they need to be able to validate this signature. And there are two components to it. So running the analysis and solving the query to produce the most permissive constraints. So it turns out that solving the query is an expensive part. And this is something that the deployer of the contract typically does offline. But validating the sharding signature is actually a cheap part. So every replica can do that. So that's why there is no risk of denial of service attack because of that. So the analysis is actually gas bound. And also it's linear time. So it's no more expensive than type checking the contract. Okay, so once the contract is stored along with this metadata, the lookup nodes can take some advantage of it and look at this metadata, solve very, very simple set of constraints to determine which shard the transaction should be routed to, and if the set of constraints is unsolvable, it goes to this DS shard, having no advantage of parallelism whatsoever, but not violating any guarantees. And after parallel processing, at the end of the epoch, all the shards merge forward the deltas of their effects into the DS shard, and this is where the merging strategies are invoked to reconcile the contributions from shards before the next stage. This is it. Okay. So we have evaluated it. So back then, when we wrote the paper, we collected somewhat like 40 representative contracts. We shown that analyzing the contract is not more expensive than parsing it or type checking it. So the analysis is actually proven to be linear time, and it's quite fast. And we also evaluated the system, the approach, by introducing a number of shards into the system and seeing how that affects throughput. So the baseline basically is the system with 3 shards, but no results of the analysis are taken into the account. There are some two interesting cases. In all other cases, we focus on one particular transition of the contract, which is assumed to be the most popular. And you see, even for 3 shards, when we enable the analysis, the throughput goes up almost 3 times as it should. And then it goes up further and further the more shards we add. So there were 2 case studies in this proof of IPFS, interplanetary file system contract, and the fungible token fund, which actually didn't benefit that much from the parallelism. And this is actually a very interesting case. So the reason why they didn't benefit that much from the result of the analysis, well, maybe a little bit marginally here, is that because of the ownership requirements. So effectively, in order to run these transactions on a shard, the constraints were such that the shard needs to own 2 pieces of state, like one entry in the map and another entry in the map. And because of the randomness, that happens not as often as we would like. So it's very rarely that we had shards that actually owned the exactly 2 pieces of states to run this transaction. So like this was unsolvable, and it was always going to the sequential processing part. And that's why for these transitions, there was not that much parallelism. So we have some idea how to address that. Let me briefly mention it now. Okay, I'm approaching the end now. So The system was the first prototype, usually raises a lot of questions with regard to more expressive models, and this is the questions that I'm happy to discuss. So the key limitations that we recognize now is that it's still kind of focused on transactions that only touch the state of one contract. So if we have a transaction that initiates the transition of a contract, that sends a message to yet another contract, and so on, now we need to do something more convoluted, and we need to collect the signatures of all these involved contracts, and also somehow we need to know for the transaction to declare upfront the chain of the contracts that is going to involve, which in many cases might be tricky because those contracts, the co-lead contracts, might be determined dynamically. So this is very difficult. It's very difficult to effectively shard those transactions. Another observation that we have made is actually from these particular transitions that we didn't manage to shard that effectively. So sometimes more than one component of the state need to be locked. And this is actually a very nice thing because this might give an opportunity for program repair. So here's one example. I'm not going to go too much into the detail, but effectively, So the example here is that we have the code on the left, which utilizes token ID as a key in the map, and then it performs the update in the map based on the other key, which was fetched based on this token. I have a really cool thing here. Okay, so we performed the fetch, and then we performed certain operation with something that indirectly was obtained by this token ID. Okay, so it turns out that this can be sharded if instead of getting the token owner from this map, we pass it explicitly as an argument and replace this fetching by simple validation that this is actually the token ID for the right token owner. And then we can shard it based on token ID. That effectively changes the ABI and the signature of the contract, but if you want to have parallelism, and there's another interesting discussion how to incentivize people to write this contract that they will be executed in parallel, this is very much an equivalent transformation that you can do, but well, it requires one extra parameter. Finally, and I know that some of you might have got this idea, well, we are talking about ownership, we are talking about linearity and effects. Wouldn't it be nice to look at other programming languages that come to popularity nowadays? So Rust has ownership embedded to it by default, and this is actually getting progressively more and more popular language for programming smart contracts. So Move, which is a language that was initially developed by Facebook but now adopted by a bunch of spin-off startups, or Rust itself are used by systems. So Solana was already mentioned. So Rust is a language that is used by Solana, except that Solana as a startup there, I don't think they're very much interested in the layer 1 parallelism story at the moment because their throughput comes from the fact that they use beefy machines. But it's always a good idea at some point to realize when we can ask programmer for the help. So one weakness of our approach is that we actually don't rely on any user annotation. So all analysis is done automatically. If we manage to add the ownership or community constraints into the types, that probably will be a big win. And with that, so in two words, what this talk was about. So that talk was about taking the ideas of parallelizing compilers and transferring them to blockchain for earning parallelism. So we have a PLDI paper last year that gives more details. In a sense, what I told today, and something that might have been new to you, is this solution to blockchain scalability problem. So this is a problem, and the solution is sharding. A solution has sharding. And the observation is sharding smart contracts is tricky, but there are opportunities for doing that. So, and this is what we call sharding smart contracts. And those opportunities might be uncovered using the traditional programming language technique called static analysis. We have done it, we have evaluated it, and we have seen an observable increase in throughput. This is all I have. Thank you.
Thank you. So we already had some questions during the talk, but we have a few minutes for more.
Ilya, thank you for the talk. So you said that you have this kind of like weak memory conditions. Do you have like any specific consistency condition in mind, or it's something custom?
Okay, so the question is about consistency conditions for this sort of protocols. I think this is a very interesting question and a largely underexplored area. So if you read the documentation of Ethereum carefully, it will give you an impression that the consistency that they promise is effectively sequential consistency. So like you don't get to see any funny effects with regard to state updates due to parallelism. And as people have known in the chip design for the last 30 years. If you want to get better throughput, if you want to get better parallelism, well, you start relaxing your conditions, but that also something that makes it tricky to program. So there are maybe a few dozen people in the world who know how to program well over C11 weak memory model. Here, if we want to make our blockchains more like parallelizable, we want to introduce the weak memory model for hundreds of smart contract developers to rely on. That has not been explored yet. I think it's a very interesting area. Does it answer the question? Okay.
Just thanks for a nice talk. I had a quick question on so these numbers that you show, did you investigate like what's the limit study of this? How much parallelism is there? First, if there is conflicts dynamically, and then in the absolute limit study when there are no, like, okay, so let's take that there are conflicts if you run it dynamically. Yep. I mean, it's some approximation, some upper bound. What's the potential?
Okay. So the question has to do is like, okay, what do we do about conflicts that happen dynamically? So you see, I don't have an easy answer to that because effectively what we optimized for is a pessimistic parallelism strategy. So we rule out conflicts whatsoever due to, and that's why we like do the disjointness and commutativity. If you have any way to resolve conflicts by doing rollback, you can probably do a little bit better. And there was some follow-up work by people from Toronto who actually tried to replicate that for Ethereum by introducing dynamic rollbacks in the case of conflicts. I don't quite remember what the numbers are, but people tried that. I think Azalea had a question.
Yeah.
Thanks, Ilya. It was a great talk. My question is also about big memory, unsurprisingly. Yeah. So specifically, you mentioned the store buffering behavior. Yeah. And I was wondering that if you have any results like we have in big memory settings, like a DRF theorem or in the distributed setting, a robustness property that says if your program satisfies this style or adheres to this recipe, then it is actually sequentially consistent.
Mm-hmm. Well, okay. I'm going to be a very boring person and say the short answer is no, but this is something that I would absolutely love to discuss. So the problem is that there is no like real like urge for introducing weak memory and specifying weak memory behaviors in the system. This is something that we observed once we tried to introduce some parallelism, but well, there was not that much follow-up in the community. But thank you for asking. Okay.
Again, great talk. For a given program, can there be multiple valid sharding signatures? And would there be a problem if different entities use different such signatures?
Great question. So what if there are more than one way to skin this cat, to shard this contract? This is why, like the question, yes, this is very much possible situation. This is why, in reality, we require this additional input from the contract developer. It's very small here. I didn't talk about it, but we spend a great deal in the paper talking about that, how you say which transitions do you want to run safely in parallel. And if you are more greedy, the more transitions that you put into the set, the stronger your constraints will be and the harder they will be to satisfy. So that's why typically it pays off to identify one transition in the contract that you want to run in parallel, something that you expect to be used a lot, and that gives you the weakest possible constraints. But if you add more, then your sharding will be poor.
Okay, any other questions? Well, I also have one. So when you explained how Zilla is different from Ethereum Solidity, for instance, right? You explained the collaboration model is different, right? You have an actor model and you don't have the reentrancy problems. So does this mean that as long as you look at single contracts, your analysis would also apply to an EVM-based contract?
Okay, question is like, can we apply to EVM if they don't have that much communication? I believe so. I mean, EVM has much more complex control flow than Scylla. That might pose the trouble. But yeah, so one key feature of Scylla that the contracts, they are very much isolated from the others. And this is what makes them easy to argue about the ownership on commutativity because there is no dependence on the state of other contracts. This is all done using message passing.
But you're ruling those out anyway, right?
Sorry?
Didn't you say in the limitations that we only look at non-collaborative contracts?
That's right. But I'm arguing that those are easier to identify in Scylla than EVM. Okay, good questions.
Thanks again for a great talk.
Thank you, Peter.